Welcome back, everyone. Today we're wrapping up our discussion of game theory, but interestingly enough, we have to start from Chapter 12 and its discussion of oligopoly. Now, I know Chapter 12 wasn't required reading. You're welcome to go back if you want to just make sure you're up to speed, but hopefully the slides will be enough. So oligopoly is a market with not lots and lots of firms, but a few firms. And in previous econ classes, you should have become familiar with the concept that in a competitive market, we get equilibrium at this point where no firm has incentive to enter the market and no firm has incentive to exit the market. Put differently, firms are earning zero economic profit in the long run, and quantity demanded is equal to quantity supplied. Now, remember that economic profit is different than accounting profit. They're still making money. They're just not losing anything on the opportunity cost. Now, what does this have to do with game theory? Oligopolies are really just strategic interactions because it's not the market setting price so much as firms setting price or output based on these strategic considerations. What are your competitors doing and what are your customers doing? And so from here, we can come up with a strategic equilibrium where firms in an oligopoly are doing the best they can based on what their competitors are doing and have no reason to change price or output, which sounds a lot like a Nash equilibrium that we were talking about last lecture. This set of strategies that constitute a mutual best response. Each firm doing the best it can given what its competitors are doing. And I've been saying oligopoly like many or a handful of firms in a market, but really we're going to talk about duopolies, markets where two firms are competing with one another. And as you become more and more advanced in your careers as economists, you'll be able to generalize to many firms. So we'll start with the Cournot model of duopoly model, in which you have two firms producing a homogeneous good, meaning the good is the same. Think of farms producing wheat, perhaps. So, and in these models, each firm is treating output as fixed, which isn't to say that output is fixed, but we're taking output as a given. And we do that as a modeling assumption to show what it looks like when you decide simultaneously how much to produce. What this means is think of two farms making wheat. The wheat from farm A is the same as the wheat from farm B. The market price is determined by how much wheat is brought to market, but we don't know how much wheat is coming to market until they show up at the farmer's market the next day. What this means is that firm 1 is going to produce based on a set of beliefs. It's going to produce based on how much it thinks that firm 2 is producing. So let's assume for a second that it thinks firm 2 is producing nothing. That just means firm 1 is a monopolist, and its demand curve will be the market demand curve. Its marginal revenue will intersect its marginal cost curve, setting an output decision for that curve. But suppose firm 1 thinks that firm 2 is going to produce something. What that means, in this case, say firm 2 is producing 50, firm 1 thinks firm 2 will produce 50, its demand curve has basically shifted in by 50 units, with a marginal revenue curve shifting in accordingly. And now we see the profit maximizing output at 25 units instead of 50 units. Remember, for all firms, regardless of market structure, profit max is just where marginal revenue equals marginal cost. And in this case, firm 1 has a constant marginal cost curve here. So we're talking about this very generally. But let's see what this looks like in practice. And from here, we'll then derive a numerical example. But basically, firm 1 knowing what it knows about the market, has decided how much it's going to produce based on whatever it thinks firm 2 is producing. In other words, we've derived for firm 1 a reaction curve, which is a relationship showing the profit maximizing output for firm 1 conditional on output by firm 2. So last slide we said, what if firm 2 produces nothing? Then firm 1 is effectively a monopolist and is going to produce 100 units. What if firm 2 is producing 100 units, or 75 units, let's say? Then firm 1 is not going to have incentive to produce anything. It's not worth the cost. Just like we derived a reaction curve for firm 1, we can so derive a reaction curve for firm 2. Which again is just a function of output, output as a function of how much it thinks firm 1 is producing. And where these two reaction curves cross is the equilibrium. The point where each firm correctly assumes the amount that its competitor will produce and sets its reaction accordingly. This is a Nash equilibrium like we talked about in the last lecture, because no firm has incentive to deviate from this point. In fact, this point is sometimes called a Cournot-Nash equilibrium. It's the equilibrium in the Cournot model, which is a model of duopoly with firms competing with homogeneous product, and so they compete on quantity. In such a model, each firm takes its competitor's production as given and sets a reaction based on that given amount. As a result, no firm wants to deviate from this equilibrium, thus it is Nash. Let's see a numerical example of how this works. We have two firms in this market, it's duopoly, and they face the following market demand curve. Price is equal to 30 minus the quantity produced. Neither firm has any marginal cost, and we'll do this just for simplicity's sake. So a firm wants to set marginal revenue equal to marginal cost. We've got marginal cost equal to 0. Let's get a revenue curve and from there derive marginal revenue. So revenue, remember, is just price times quantity. We're given market price, 30 minus Q. But remember, this Q is market quantity. It's the total quantity produced by both firm 1 and firm 2. So how do we get an individual firm's marginal revenue from there? Well, we plug price times quantity into this market price, and we also plug in quantity of firm 1 by quantity plus quantity of firm 2 into this total quantity equation. So revenue, and we're going to say for firm 1, but it's equivalent, is price times quantity. Price is 30 minus Q. And Q is Q1 plus Q2. And we're only talking about revenue for firm 1. So 30 minus the quantity Q1 plus Q2 times Q1. Multiplying this all the way out, we have 30 times Q1 minus Q1 squared minus Q1 times Q2. You can take a minute to go through this algebra on your own. But from here, we can derive, both in the metaphorical sense and the mathematical sense, we can derive marginal revenue. So dr dq is marginal revenue. That's just the derivative of this revenue curve. So 30 minus 2q sub 1 minus q sub 2. And it's our job to set, remember, marginal revenue equal to marginal cost, which in this case is 0. So MR equals MC, 30 minus 2Q sub 1 minus Q sub 2 equals 0. From here, since firm 1 is taking firm 2's production as given, we can solve for Q1 as a function of Q2, which we have here. We'll note that since firms have equivalent marginal cost curves, and they face the same market demand curve, their reaction curves are equal. So by the same math, Q2 equals 15 minus 1/2 Q sub 1. We can then get the Cournot equilibrium by substituting Q2 star into our formula for Q1. Take a minute to do that algebra on your own, but you should get that both firms in this numerical example produce 10, putting the market quantity at 20, giving us a market price, P star, of 10. What if the firms weren't competing? What if they were colluding, which we should note is illegal? If the firms were colluding, they'd effectively be functioning as a monopolist. We'd still have the same market demand curve, but then total revenue, we don't have to take the other quantity as given. There's just one quantity, the monopolist quantity. Total revenue is 30Q minus Q squared. Deriving that, we have 30 minus 2Q. So total profit is maximized at Q equals 15. I'm going over this really quickly, but just take a minute on your own to press pause and do the algebra. So any isoquant, the isoquant where total production is 15, is the collusion curve. If the firms are splitting profits equally, they'll each produce 7.5. But we'll note that in such a case, 15 total units produced, 30 minus Q, implies the monopoly price, P sub M, equals 15. If the firms are colluding rather than competing, we're getting price gouged. We're paying more for, in this case, I believe I said wheat. What does this look like? Well, if each firm colludes and produces 7.5 at a market price of 15, they're making $112.50 in revenue. Oops, let me clear that up. If each firm produces 7.5 at a market price of 15, they're making $112.50 in revenue, whereas if each firm produces 10 at a market price of 10, they're making $100 in revenue. So the firms want to be able to collude, but of course they can't. It's illegal. And we see here in this graph that going from a monopoly pricing scheme or an illegal collusion scheme to a competitive equilibrium to a perfectly competitive equilibrium where price equals, where market price is flat, we as the consumer are doing better and better and better. In the Cournot model, firms are competing on quantity, and the amount produced determines market price. So if we use the same market demand curve as last example, but now set marginal cost, instead of having it equal to nothing, equal to 3, each firm will produce 9 in Cournot equilibrium, resulting in a market price of 12. So each firm will make a profit of $81. Press pause and go through the algebra of this on your own, but that's not what we want to talk about on this slide. We want to talk about what if they're not competing on quantity. But what if they're competing on price instead? Well, in this Cournot example, we had each firm charging a market price of 12 based on the quantity they produced. So again, let's consider the case of two farmers producing an identical crop. One is coming to market with a $12 crop. The other has the exact same crop but is charging you $11. What happens? No one wants to buy the $12 crop. So in a Bertrand model where firms are competing on price, the firms will outbid each other on price until we get to price equals marginal cost, with firms earning zero economic profit. And effectively, even though we only have a few firms in this marketplace, even though we're in a duopoly world, we as the consumer are treated as if it's a case of perfect competition. So last time we were talking about the hoteling competition where we choose where we want to compete, compete based on location. Bertrand competition, where we compete based on price, is very similar, because you don't care whether you go to FedEx or UPS, you just want the cheapest way for your package to get to point B. And in doing so, the consumer benefits, and the firms make zero economic profit. That was a nice way of revisiting how this new theory that we've learned, game theory, can apply to, industrial organization and various market structures. Let's return to chapter 13 and add some complexity to the ways in which we view games. And specifically, we've been looking at games that we call simultaneous games, games in which players make their decisions at the same time. But we know that in the naturally occurring world, this doesn't always happen. Sometimes some people get the benefit of deciding first. And we model these games as sequential games, games in which players move in turn. And this is actually more similar to what you might see in gaming in the sense of playing games, right? When you're playing Monopoly, you roll the dice and move your piece forward, and the next player gets to see that and react to it. In a minute, we'll take the Cournot duopoly model that we talked about earlier, where firms are competing on quantity, and see what happens when you know the other player's quantity first. But for now, let's just talk about sequential games more generally, where you can think through the possible actions and reactions of each player in a systemized way. So last lecture, we talked about the product choice problem, where you can introduce a crispy cereal or a sweet cereal. And if you introduce those cereals at the same time, we're likely to land in a situation where both firms introduce sugary cereals, flood the market, and we all lose money. You'll note these payoffs are a little different than the one we looked at last time. But now let's modify the game not in the sense of payoff modification, but rule modification, where firm 1 will move first, and firm 2 will get to choose which cereal they introduce based on firm 1's move. We can depict such a sequential game with what's known as a game tree, otherwise known as the extensive form of the game. So again, we have firm 1 as the first mover. Firm 1 can either choose to make a crispy cereal or a sweet cereal. We call each of these points nodes, and from these nodes, we can see firm 2's choices, where they can either choose to make a crispy cereal or a sweet cereal. Similarly, if firm 1 makes a sweet cereal, firm 2 has the same choices, crispy or sweet. This ends the game, firm 2's choice ends the game, and we can see the payoffs based on both firm 1 and firm 2's choices at the end of this game tree. Now, these are the same payoffs from the table on the last slide, but the fact that the game is now sequential means that we can visualize possible moves a little bit better, and we can also backward induce. So when we have a sequential game, we start at the end. We start with these payoffs, and from here determine firm 2's best response, and from there determine firm 1's best response. We'll then fast forward to firm 2 to double check our choices. So let's assume that we're in the firm 1 produces crispy. We're in the crispy world. From here, firm 2 can produce crispy or sweet. If firm 2 produces crispy, they get -$5. If firm 2 produces sweet, they get $20. So of -5 and 20, firm 2 obviously prefers sweet. I'm going to switch the color up, but similarly, let's assume that firm 1 produces sweet. From here, firm 2 can produce crispy, or they can produce sweet. If firm 2 produces crispy, they get $10. If firm 2 produces sweet, they get $5. So firm 2 prefers to produce crispy and get $10. Firm 1 is forward-looking and knows this. So firm 1 knows that if they produce crispy, firm 2 will produce sweet, and firm 1 will get $10. Firm 1 also knows that if they produce sweet, firm 2 will produce crispy, and firm 1 will get $20. So looking at a choice between $20 and $10, firm 2 prefers to produce sweet and make $20. Firm 2 prefers to produce crispy in response to that and make $10. Everyone loves sugar cereals. What we see is two things. One, firm 1 has what's known as a first mover advantage. Firm 1 does better based on the fact that they're able to produce first. And two, we're able to backwards induce and make rational decisions from there. Now that we're all expert in game theory, let's add some complexity to it, and let's look at a duopoly model where firms have, in this case, 3 choices of output. See if we can find first a mutual best response, and then add some sequentiality to it. So if firm 2 is producing 7.5, firm 1's best response is to produce 10. If firm 2 is producing 10, firm 1's best response is to produce 10. And if firm 2 is producing 15, firm 1's best response is to produce 7.5. Let's flip it up real quick. If firm 1 is producing 7.5, firm 2's best response is to produce 10. If firm 2 is producing 10, firm 2's best response is to produce 10. And if firm 1 is producing 15, firm 2's best response is to produce 7.5. So we see here a mutual best response in the simultaneous version where both firms are producing 10. This is the Cournot duopoly model. But let's take Cournot rules where firms are competing on quantity and give firm 1 the, let's call it a benefit, of announcing their move first. Let's see how that changes. We call this a Stackelberg model. It's a model in which one firm sets output before another firm does. So let's give that same example. 2 firms bringing some crop to market, 2 farms bringing a crop to market. But for whatever reason, farm 1 lives a little bit further away and has to bring their crops the night before, which gives farm 2 the advantage of seeing what they're doing. So let's take the same linear demand system in a duopoly model that we started this lecture with. Just to refresh everyone's memory, price is 30 minus market quantity, and neither firm has a marginal cost. So before, this gave us a symmetry in the firm's reaction functions, where both firm 1 and firm 2 previously had the same reaction curve, 15 minus 1/2 the quantity of the other firm. But now, since firm 2 is moving first, we can backward induce, like we did with that game tree, and set firm 1's revenue, this is the same revenue function we had before, but plug in firm 2's reaction curve to that revenue model. So plugging in, we get 15Q1 minus 1/2 Q1 squared. We can derive firm 1's marginal revenue from there and get 15 minus Q1. Remember, we have no marginal cost, so setting marginal revenue equal to marginal cost gives us firm 1 producing 15, as opposed to the 10 they were producing in the Cournot model. And now that firm 2 knows firm 1 is going to produce 15, they don't want to flood the market. Firm 2 is producing 7.5. In other words, firm 1 is producing twice as much as firm 2 and makes twice as much of a profit. Going first gives firm 1 the advantage. Take a minute to go over the algebra of this on your own, and we can talk about it more in class. But that's all there is for game theory. I'll look forward to finishing up the semester with you when we talk about information economics.